For example circuit number 12, we're going to be looking at a shift register, which is a way to multiply the number of outputs that you can control from your Arduino. Essentially, a shift register allows you to take 3 output pins and use them to control multiple more outputs. This example will use 8 LEDs from 3 pins as opposed to 8 LEDs with 8 pins. You can also get larger shift registers, which would be able to control even more outputs with the same 3-pin input. So we're going to head over to the schematic now. And over here in the schematic, we've got our shift register, which is this guy right here. Shift register looks a lot like a little computer chip. It's got a notch in the top to indicate which side's up, and then the pins are numbered going counterclockwise starting from the top left. So the top left pin is 1, and then going down the line 2, 3, 4, 5, 6, 7, 8, and then across the bottom to 9, 10, 11, 12, 13, 14, 15, 16. So the various pins are all numbered starting from the top left, going counterclockwise, remembering that the top of your shift register is marked by a little notch. And it's easiest to sort of wire up your shift register using pin numbers. And so we'll start with some of the pins that have to be connected to specific portion or specific things like the plus 5 volts or ground. So pin 16 and pin 10 need to be connected to plus 5 volts. Pin 13 needs to be connected to ground. And pin 8 down here also needs to be connected to ground. Now, as far as our inputs to the shift register go, pin 14 is the data reception line, and we're going to be connecting that to pin 2 on our Arduino. So the data goes into the shift register from pin 2 on the Arduino. Pin 3 on our Arduino is the clock, and that connects to pin 12 on the shift register. So we're controlling the clock from pin 3, the data from pin 2, and pin 4 is the latch. And the latch is going to be connected to, got a mistake there. Clock does not connect to pin 12. Clock connects to pin 11. So clock controls go to pin 11, and then the latch goes to pin 12. So we've got our data, our clock, and our latch. So data goes into 14, clock goes into 11, latch goes into 12. Data is where we feed in a string of zeros and ones that the shift register will then disseminate to its various other pins as off or on signals. The clock matches the speed of our shift register to the speed of the input, so it knows, so that it can basically time those inputs to know where they're supposed to go. And latch is basically a trigger. When you flip the latch signal, it then sends out the signal from its various other pins. It's the confirmation that, okay, everything's in place, go ahead and sort everything out. So as for the actual outputs, we're connecting pin 15 on the shift register to our first LED. Pin 1 goes to our second LED. Pin 2 to the third, and so on and so forth down the line. Second goes to the 8th LED, pin 6 goes to the 7th LED. So pin 15 is connected to our first, and then pins 1 through 7 are connected to LEDs 2 through 8 in that order. And that's how we've got our entire shift register hooked up, and we're pulling plus 5 volts and a ground connection also from our Arduino in order to power our shift register and serve as the ground point for all of our resistors and the shift register itself that needs a ground point to compare to the VCC in order to know that it's receiving the right values in certain places. So you've got your shift register all wired up. Now it's time to head over to the sketch. So we've got our shift register sketch. And the first thing that the shift register does is it defines our data pin as 2, our clock pin as 3, and our latch pin as 4. So making those global variables that we can use them later. And then it defines a variable of data type byte, which is essentially 8 bits, so a string of 8 ones and zeros, and sets it to 0 for the time being at the start of this all. During the setup, we set our pins to output so that we can send data out to the shift register through them. And then we head over to the main body of the diagram, or the main body of the sketch. And the sketch has multiple different methods for lighting up the various LEDs. We've got one after another, we've got one at a time, ping pong, random LED, marquee, and then binary counting. So each of these is going to call their own program, but first we need to look at this shift right function that they've given. So void shift right is going to be called by all of these various other functions to determine or to actually send the information to our shift register. And it's going to be receiving 2 pieces of information, an integer, which is a desired pin we want to affect, and then Boolean, so a yes/no, what state do we want to put it into. So first the first thing the program does is takes the global variable data and changes the bit in data to a 1 or 0 that we want. So bit right, the first parameter is data, so the variable we want to bit right to, desired pin, so which bit in the variable data do we want to change, and then desired state, what do we want to put it into. So that takes those 2 bits of information that we received, or those 2 pieces of information we received, desired pin and desired state, and uses them to alter the data variable accordingly. Next, they have to send the information to the shift register, and the Arduino has a function that does exactly that. Shift out. This automatically encodes the information to be sent out to a shift register and needs the following parameters. Data pin, the data pin you want to send it out on. Clock pin, the clock pin that you're using to time the shift register. What order you want to send them in. And there's two possible options here, MSB first and LSB first, and those stand for most significant bit first and least significant bit first. We're using MSB first for this code, and that simply means read from left to right. If I were to use LSB first, it would read from right to left. So where I'm sending these out to LEDs, basically the only thing that MSB first and LSB first changes is order. If I write using MSB first, and then I switch this to LSB first, the order of the lights will change. Light 1 will suddenly become light number 8, light 2 will become light number 7, and so on and so forth. It basically reverses the order that it steps through them. And then data, which is the data we want to send via shift out. So we send the data to the shift register, and it's in the shift register. And in order to get the shift register to actually send the data out to our LEDs, we need to toggle the latch pin. So we digital write our latch pin high and then low. And when we do that, we basically toggle the latch pin on our shift register, and it takes that signal to mean send my data out to the things I'm connected to, in this case LEDs. So that's how we write things out to our shift register. So now if we look at one after another defines index and delay time, and to turn all the LEDs on, it uses a for loop where index starts at 0, goes to 7, and increases by 1 each time, and it wants to shift right index high. And shift right goes back up to this function, so it's receiving index as desired pin and high as desired state. So it's going to go into that byte variable and set the bits from 0 to 7 as high. And it's going to do that in order from 0 to 7 with a delay of delay time between each time it sets one to high. So this should light up LED 1, and then 1 and 2, and then 1, 2, and 3, 1, 2, 3, and 4, and so on and so forth down the line. Next, it turns all of them off in reverse order using a for loop. For index starts at 7, goes to 0, decreases by 1 each time, using the same shift right function, sending it index and low. And in between each time sending one, also waits for a delay time. So if we head over to our actual circuit here, all hooked up nice and neat, first, here is a shift register that's not actually plugged in. As you can see, it looks a lot like a little computer chip. There is a little semicircular notch up here at the top, and that indicates that that's the top. This pin up here would be the top left, so that's pin number 1, which makes its counterpart pin number 16. So that's a shift register. We've got our LEDs hooked up in a nice line. Okay, so we're going to send it over our sketch one after another. As you can see, the LEDs light up in a line, starting from this one here, which is number 1, going out to this one here, which is number 8. So that's the one after another. Next, we're going to look at one at a time, which should be very, very similar to the one after another code, except instead of turning them all on and then turning them all off, one at a time should include, it'll include turning the LED off as part of the for loop. So it's going to go from 0 to 7, increasing by 1 each time. It's going to turn on 1, wait, turn off 1, move to the next one in the loop. So, one at a time, upload the sketch, and it goes one at a time from 1 to 8. So next is ping pong, which is one at a time, except it should go from 1 to 8 and from 8 back down to 1. So ping pong defines index and delay time, and for index starts at 0, goes to 7, increases by 1 each time. Turn 1 on, wait, turn 1 off, go through the loop again, 2, 3, 4, 5, 6, 7, 8. And then for index starts at 7, goes to 0, decreases by 1 each time, turn 8 on, wait, turn 8 off. So it should go up the line and then back down the line. Let's upload the sketch for this. And it's going to go up the line, starting from 1 to 8, and then back down the line from 8 to 1. Next one we're going to look at is random LED. So that should turn on a random LED. Random LED defines index and delay time. It defines index as being a random of 8, where it picks a random number between 0 and 7, turns that one on, waits, turns it off. So it's going to create a random series of numbers and turn them on in that order. Once again, this is going to be a semi-random series of numbers, or a pseudo-random series of numbers, in that it will be the same random series of numbers every time I run this program, unless I change the random number seed. So if we go over to the circuit and upload, it blinks a bunch of random lights, but if we upload again, and it seems to start with 8 and then dance around, so we upload one more time. Yeah, it's the same pattern every time. It's a bit harder for me to catch. Yeah, it seems to go 8 to something else. So, again, 8 to 3. So it's always doing the same set of supposedly random numbers, because it's pulling from the same seed each time. The next one in the sketch is going to be marquee, and that's going to have scrolling lights. And for marquee, int index delay time defined. For index starts at 0 and goes to 3, increases by 1 each time. Turn on 1 and turn on 5. So turn on the first one and then skip ahead 4 and turn that one on as well. Wait, and then turn both of the ones that you turned on off. So it should light 1 and 5, 2 and 6, 3 and 7, 4 and 8, and then back to 1 and 5. So if we go back over to this and then run, it should be a pair of lights blinking down the line. So as you can see, each pair lights up, and that just scrolls down the line. Now the last one here does something a little bit different, and that's going to display it's going to use our 8 LEDs as essentially a binary display, and it's going to count up to 255 using our LEDs as bits. So first we define a delay time, and then we send shift out, data pin, clock pin, MSB first, data. And then we toggle our latch so that it actually goes out. And so data starts at 0, so the first thing it's going to send is 0, which would turn all of the LEDs off if any of them are on. And then it's going to toggle our latch pin, and then it's going to increase data by 1, and then wait so it doesn't simply blink through all of them faster than you can see. So data is going to increase by 1, changing it from 0 to 1, and that number is going to be stored as a byte, which is essentially the same binary information that's going to be displayed by our LED. So this is just going to show binary numbers from 1 to 255 for as long as I'm willing to let this run. So if we switch back over to this and then upload this particular sketch, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on and so forth. So this is basically just turning your 8 LEDs into a binary counter. And that's another application for something like this. You can use it to display binary information in a way that's a bit more visible than just strings of ones and zeros. This is the same sort of strings of ones and zeros, except the 1 is lights on and a 0 is lights off. So that's how you can use your shift register in order to essentially multiply the output pins on your Arduino. So suddenly your limited number of output pins can be used to control far more different sensors or far more different outputs than you have pins. Additionally, shift registers also work in reverse. So this is currently serial to parallel. It takes a string of ones and zeros and disseminates them out to a whole bunch of different ports and displays it so you can see them. You can also rig up this same shift register to be parallel to serial, where it would receive data from these various ports and then convert it to a string of ones and zeros and feed it into your program. So you can use the same shift register to multiply the number of inputs you can receive in just the same way that it can multiply the number of outputs. And that's the power of shift registers for making your Arduino with its limited pins go much further.